In this video, we're going to come up with equations for planes like this. And it's going to sort of extend the work that we did previously on equations for lines. Now, when we did equations of lines, I had to give you a couple pieces of information. I had to give you a point on the line, and I had to give you a direction vector along the line. And the same basic idea is going to be true for planes as well. And I had to give you two pieces of information, but they're a little bit different. The first of them might be the same. I need to give you a specific point on the plane, some x naught, y naught, z naught that lives on that particular plane. And then, after I fix that it goes through some specific point, I have to give some other piece of information that tells how do you tilt or sort of orient the plane in 3 dimensions under the condition it goes through that one specific point. So, the piece of information here I'm going to give is one of the choices for a normal vector. A normal vector is a vector that points directly away from the plane. And indeed, if I tell you the normal vector, that in some sense tells you the orientation of the plane. I'm going to go really low-tech for a moment. I've got a plane by a piece of paper and I've got some pen. The pen is the normal vector, so it's sticking straight out at a 90-degree angle. And then if I have different planes, as I twist and tilt it around, the normal vector, it twists and tilts along with it. So then, if I have those two pieces of fixed information, a fixed point and one of the normals, I want to try to describe all of the points on the plane. So let me just take some other generic point here, this p of x, y, z. This is a generic point on the plane thought of different than the fixed specific point, the x naught, y naught, z naught. Well, there is a vector that goes from the p naught to the p. It's this red vector I'm putting here. And what I meant precisely when I said that it is a normal vector to the plane is that it is orthogonal with any vector that is lying in the plane. So this normal which sticks straight out of the plane and this p naught to p vector that lives in the plane, that those two vectors are going to be orthogonal or that their dot product is 0. So I have the following constraint. It's that this normal vector dotted with the vector that goes from p naught out to p, that has to be orthogonal, aka the dot product is 0. And then, if I leave my fixed point where it is, but I move where the p is, for example, if I consider this different location or this different location again, well, in all of these scenarios, you have this p naught to p vector being orthogonal to the n vector. So indeed, this is going to be my equation of the plane, is that the normal dotted with any vector line in the plane, any p naught out to p, is going to be equal to 0. Let's see how this works out in a specific example. So I'm going to choose the specific point, p naught is equal to 1, 2, 3, and the normal vector, the vector perpendicular to the plane, 4, 5, 6. Now, the one hard part to think about is what is the p naught to p vector? P naught is that point 1, 2, 3, but p itself is going to be a point x, y, z. So if I take the vector that goes from p naught out to p, what this is going to look like is, well, in its first component, it's going to be x minus 1, the first component of p naught, y minus 2, the second component, and then finally z minus 3. Okay, now that I know the p naught to p vector, I can take their dot product of these two things. The dot product is the sum of the first two components multiplied, then the second two components, and the third two components. So if I expand all of this out, I'm going to get this 4x minus 4 plus 5y minus 10 plus 6z minus 18 is equal to 0. This equation, by the way, is called its component form in contrast to the vector form that we have at the top, the n vector dotted the p naught to p vector. And then if I want to take this component form, I can see that there's actually a bunch of coefficients, the minus 4, the minus 10, the minus 18. I can move those all to the other side in the simplified component form of it, and I get 4x plus 5y plus 6z is equal to 32 if I've done my math correctly. So the big story here is that if I had a line and I gave you a point in the direction vector, that was going to give you the equation of a line. And for a plane, if I give you a point on the plane and the normal vector, or a normal, because there's many of them, a normal vector to it, then you can write out the equation of the plane.